So today I would like to finish off the section of Fourier Transform that we started. I'm going to change a little bit what I left off with last time. I'm not look at that particular solution of Green's function. So we were looking at the Green's function for the wave equation. I would like to change that a little bit and still look at the Green's function, but the Green's function now for the spatial part of that. So this is the Poisson equation. Okay. So we're still trying to illustrate the utility of Fourier transform, solving differential equations. The properties are going to be the same, but I realized that I want to move on to the last transform. The other one's going to take at least 2 lectures to describe its detail. It's a necessary part of the course on string theory that we're doing solid block, so I will be covering that material there. It's also required for anybody who wants to go over it. I'll refer you to those lectures. But so the point I'm trying to make, which is that the Fourier transform is a useful way of solving differential equations. This will do, without all of the details that go into solving our poles and line real axis, etc. All right, so here I would like to compute the Green's function associated with a Coulomb interaction. And essentially, so suppose we were to solve following equation. So here, I'm going to calculate the Laplacian of some function, let's say phi, equal to 0. This is the Poisson equation. So the Laplacian of the function is 0, and I would like to know what that function is. I mean, ideally, I want to throw in some right-hand side source term and compute things there. And we're going to approach this in 2 ways. One is I'm going to assume cylindrical symmetry, spherical symmetry in, let's say, 3 dimensions. So I'm going to assume 1, t equals 3. So this could be the Cartesian form of the Laplacian operator, second derivative with respect to x, second derivative with respect to y, second derivative with respect to z, acting on phi. It could also be written down in polar coordinates. So derivatives involving phi, theta, and r. But I'm also going to assume spherical symmetry. So if I assume spherical symmetry, that means that nothing depends on any angular variables. There's no angular dependence involved, which means that this whole story here just becomes the differential equation in R. Which makes our lives a hell of a lot easier. In particular, I want to use these 2 assumptions. T equals 3 is not a big deal, but this gives us a lot of constraints to help us solve the problem. And I'm going to solve this using the method of Green's functions. So we would like to solve this equation using So the associated Green's function is called, let's call it G. G will be a function of R and R prime. So position vector R and R prime. Remember, last time I said that the Green's function was a response function of the system. So this phi here describes some physical system. Right? I act on it with a differential operator, and that gives me 0, but it could also give me some non-valuation. Right? So Green's function is the inherent response of the system when acted upon by this same differential operator, but with the impulse source. So it does the function source. So this guy here satisfies the same equation with the same boundary conditions. Should I stipulate such boundary conditions? I'm going to denote this by del squared r, so I'm going to be working in spherical coordinates. It solves g del squared acting on g of r prime equal to delta r minus r prime. So we would like to solve this differential equation, and we're going to approach solving this differential equation by Fourier transform. So a Fourier transform this equation, and I find that this is just Fourier transform of del squared g. Fourier transform, every time del squared acts, it acts on the r, it pulls down factors k, ik. I get two factors of ik. Yeah, ik. So I get two factors of ik, so that's minus k squared. Really, what I mean here is k dot k times g tilde. This will be a function of k r prime. Because I'm doing Fourier transform with respect to r. On the right hand side, I get the Fourier transform of the delta function. So that's 1 over 2 pi 3 halves times e to the I k dot r prime. And this is an algebraic equation in k space. And so I can solve for the Fourier transform of the Green's function. So g tilde of k r prime is minus 2 pi minus 3 halves to the I k dot r prime over k squared. And then, as the algorithm goes, what I need to do now is to invert this Fourier transform. So if I invert the Fourier transform, I'll find that g of r prime is minus 1 over 2 pi 3 halves integral over 3-dimensional real space of e to the minus I k dot r minus r over k squared d3. Well, at this point, you could do the integral. But you can also realize that this thing is nothing but 1 over 2 pi d halves times the inverse Fourier transform of 1 over k squared. And so if I know how to invert 1 over k squared, then I know how to get the Green's function. And again, there are two ways of doing this. The first way, the brute force way, is do the integral. It's a complex integral. You have to do the complex integral, and I'll up whatever you're shooting for. So that's the one way of doing it. The second way of doing it is use the result that we already know, which is what the Fourier transform of Coulomb interactions. This is why I said this is the Green's function associated with Coulomb. So to compute this, we'll recall that the Fourier transform of 1 over r was 2 over the square root of 2 pi times 1 over k squared. And remind you, the way we did this was this integral was the integral that comes in this Fourier transform of 1 over r Coulomb interaction was divergent, and where we cured it. Circumvented that divergence was we multiplied this by some exponential envelope that cut this thing off so that the integral converged. This was the alpha interaction, e to the minus alpha r. We found the convergent integral associated to that, and then we set alpha to 0. Right? So we turned off the regulator. And that gave us this here for the Fourier transform. Well, what this means is that the inverse transform of 1 over k squared is what I get when I act with the inverse transform as an operator, as an integral operator on the left hand side and the right hand side, is just root pi over 2 times 1 over r. That's exactly what we want, and I didn't even have to do the integral because we've already done this integral before. But what it means is that g of r prime is then simply minus 1 over 4 pi times 1 over mod r minus r prime. And one thing you'll notice from this is that you can automatically see that g depends only on the difference between r and r prime. This is how that difference enters the story. So the Green's function associated to the Poisson equation is simply 1 over r minus r prime. Okay. And given this Green's function, you know that this is the inherent response of the system to any given that this is the inherent response of the system to any perturbation, which would be the right-hand side here, once I know what the Green's function of the system is, I can immediately solve the Poisson equation with any right-hand side that I want by just multiplying that Green's function and then integrate. Okay. All right. Realize there's one more thing I wanted to tell you before going on to the transform. This lecture might not actually have to do with the cross transform at all. Let's see how it goes. And that's to give you a phase space formulation of the Schrodinger equation for quantum mechanics. Right. So, and the Fourier transform really plays an integral role in this. This will give us a taste of the theory of integral equations that is to come. Right. So, okay. So let's just take a step back and see if we give an overview of what quantum mechanics is really all about. Let's say as applied mathematicians rather than as physicists. So I'm not interested in all of the really super interesting physics that's associated to quantum mechanics. But if I wanted to approach the problem as an applied mathematician, then essentially I go back to classical mechanics. And classical mechanics is about geometry. It's about a particular type of geometry called symplectic geometry. This is the geometry of phase space. So I can describe any system, any classical system, through a set of equations of motion. Those equations of motion are essentially Newton's laws. And I can formulate Newton's laws as a particular class of equations that arise from Hamilton's principles, Hamilton equations. So Hamilton's equations, Hamiltonian that's associated to it, is really the central aspect of classical. So classical mechanics is all about symplectic geometry of phase space. I think that's the dynamics. Corresponds to symplectic geometry. By the way, who did differential geometry? Okay, so this is called symplectic geometry because there exists a certain. How far did you guys get to do differential forms? Stop just before differential forms. Okay. So symplectic geometry is geometry that's in space of a particular manifold that's equipped with a particular form, or a symplectic form, and symplectic form is constructed from position variables and momentum variables. So this manifold on which classical mechanics takes place is phase space. And so it's coordinatized by position variables and momentum variables. So for an n-dimensional classical mechanical system, the symplectic manifold is a 2n-dimensional manifold, a 2n-dimensional space, locally it looks like flat space, and it's equipped with a particular form, which gives it all of the mathematical structure that you know already in classical mechanics, but maybe not in this language. And that structure comes from this thing called symplectic form. It's a beautiful, beautiful theory. This is obviously not how Newton and all these guys thought about classical mechanics, but today this is how we realize the idea of classical mechanics. The point of this manifold is that in this space of, in this phase space, if you want, every point is coordinatized by some set of position variables and some set of momentum variables. And classical dynamics is really about geodesics, minimal distance paths on this phase space. This is classical phase space. And the position and momentum variables satisfy Hamilton's equation. To go from classical dynamics to quantum dynamics, you quantize the theory. You quantize classical dynamics by essentially making this classical manifold noisy. What this means is that you can no longer resolve a given point in the phase space. The space becomes fuzzy in some sense. In a very precise sense. The precise sense is that the uncertainty in measurements of where you are, delta x times delta p, must be greater than or equal to h bar. Right? This is nothing but the Heisenberg uncertainty principle. So the Heisenberg uncertainty principle stated in this geometric setting is that, if I want to tell you where a particular point in space is, I define for you some coordinate system. And I say, well, you move x units in this direction and p units in that direction, and I'll get to this point. Okay. These are vectors, so you're going to move in different dimensions. But I move x units in this direction, p units in that direction, I'll get to this point. But you'll also get to the same point if you move p units in this direction and then x units in that direction. Okay. Same is no longer true in a quantum space. In a quantum space, delta x times delta p not being 0 means that if I move first in this direction and that direction, then this direction and that direction, I'll get to different points. So I can't resolve a point to infinite precision in quantum mechanics. So essentially, the way you quantize is you take these variables x and p, which in the classical space satisfy that the Poisson bracket between them is non-zero. Okay, no big deal. This gets promoted to something called the Heisenberg algebra that the x's and p's have to satisfy. This is nothing but commutation relations that you would have heard about when you first learned quantum mechanics. Right? So this is the Heisenberg algebra. This means that x and p ought to be thought of not as classical numbers, but as operators. Operators are acting in some delta space, some space of functions. Okay? And the dynamics of any quantum state, any function in this Hilbert space is governed by the Schrodinger equation. The Schrodinger equation you're familiar with says that I times h bar, Planck's constant, times the derivative with respect to time of the state psi as a vector, this is a ket level space, is the Hamiltonian acting on that state. And this thing has a time-independent formulation as follows. So if I take this vector and write it in this basis, then I get the following equation that basically says H psi and the Hamiltonian standard form is p squared over 2m plus some potential function of x. The hat here indicates that these are all operators. Psi is psi. It becomes an eigenvalue equation where this guy psi of x projection of the vector psi to the vector x. And this operator P here is minus I d by dx. So here I've chosen the x basis to project the vector psi. But there's really nothing preventing me from defining psi, projecting psi onto the p basis, the momentum space basis. And then the question becomes, well, what does this equation, which is a second order differential equation in x, look like in p basis? What does the Schrodinger equation look like in conventional basis? This is not usually the way physicists would pose the problem and try to solve various physical problems. Okay. But as we'll see when we go to the theory of integral equations, there are certain advantages of doing it this way. So what does the Schrodinger equation look like? P basis. So to answer this question, suppose that I take the Fourier transform of my wave function psi of x. I'll get something that depends on momentum, just p. So I'm going to assume, and I'm going to call this guy phi of p. Right? And we appreciate that I can extend this to any number of dimensions I want. So let's just work in one dimension. So suppose that phi of p is a Fourier transform of psi of x. This question, what does the Schrodinger equation look like in the p basis, can be reformulated as what equation does this guy satisfy? Okay? Is everybody with me? So this thing phi of p is 1 over square root of 2 pi times the integral. Again, I'm working in one dimension, minus infinity to infinity, phi psi of x e to the minus e to the plus phi d x dx. Similarly, psi of x is the same thing with a minus sign. So I'm going to make one more definition, and that's I'm going to write the potential v of x as 1 over root 2 pi integral of some associated w of k, w of p in momentum space, e to the minus phi dx. So this here is the Fourier transform of the potential. So now if I apply the Fourier transform to the time independent Schrodinger equation I have here. So if I just Fourier transform across, I get 1 over root 2 pi. This will be common to everything that's good. So I'll take it out. The first term will give me a 1 over 2 times the mass integral minus infinity to infinity of p squared e to the so basically I'm writing phi as the inverse Fourier transform. So this will be p squared, phi of p e to the minus I dx dp plus 1 over root 2 pi, because I have a potential that I'm inverse Fourier transforming, and I also have this psi that I'm inverse Fourier transforming. Each of those comes with a factor of 1 over root 2 pi. I've taken 1 out, so there's 1 remaining, but I want to get for a purpose. Integral minus infinity to infinity p integral minus infinity to infinity dp prime e to the minus I dx e to the minus I d prime x w d prime phi e. And then finally, this minus times the integral minus infinity of phi e to the minus I dx, which I integrate this to p, all of that is equal to 0. So in this, I will have an exponential that I write as e to the minus I e plus e prime times x. And I'll call this thing, let's say, p double prime. Change variables, and then I'll relabel this thing as p. So I'm missing out a couple of steps here. Essentially, it's recasting this integral as an integral over p double prime and then relating that as p. So if I do that to the double integral, I want you to fill in the steps. Then I find that the integral from minus infinity, dropping this factor of 1 over 2 pi into 0 in any event, of e to the minus I p x of p squared over 2m minus e times phi of p plus 1 over the square root of 2 pi times the integral minus infinity of w of e minus 1 phi dp prime respect to p. Well, the only way that this is equal to 0 for all values of x is if the thing in curly brackets is equal to 0. In other words, p squared over 2m minus e phi e plus 1 over root 2 pi integral e minus phi prime The difference between this equation, so this is the momentum space version of Schrodinger equation. The difference between this and this Schrodinger equation is that this is a second order differential equation, involves derivatives. This thing involves the function that we're trying to solve for, y of p, and its integral. Okay, so this is an example of an integral equation, as opposed to differential equations like this. Question? So let me do one example quickly to illustrate how to use and we want to use this to compute the energy of the 1s orbital in appropriate units, natural units are H plus equals 1, of the hydrogen atom. So the hydrogen atom consists of a single proton orbited by a single electron. So an electron has some energy levels. We want to calculate those energy levels are labeled by 1s, T, things you learned about mass. We would like to calculate the energy of the 1s orbital of this hydrogen atom. So when the electron is in the 1s orbital of the hydrogen atom, what is its energy? So the electron is held in orbit around the proton by the Coulomb. Okay. So the Schrodinger Equation. So the time-independent Schrodinger Equation for this problem, in units where the mass is set equal to 1, del squared psi r minus 1 over r psi of r this three-dimensional problem. This is the Coulomb interaction. This is the energy we want to calculate. I'll write down what the wave function is for the 1s orbital. So we don't want to calculate this for an arbitrary psi. We want to calculate it for a very specific psi. So I can write that down. So psi of r for the 1s orbital e minus r. Okay. So the first thing is I know what the Fourier transform of. So let's Fourier transform this equation. I know what the Fourier transform of 1 over r is. Fourier transforming using the fact that Fourier transform of 1 over r is 1 over 2 pi d halves. Now d dimensions 4 pi a squared. And writing the Fourier transform of this psi of r as some phi of k, we'll find that k squared over 2 times phi of k minus 1 over 2 pi cubed times the integral of the dphi a prime 4 pi over k minus prime squared times phi of k prime. So I've integrated this with k prime. All of this must equal to e phi of. If this is the orbital of the 1s, sorry, this is the wave function of the 1s orbital, its Fourier transform phi of k is the Fourier transform of this decaying exponential. Calculate this quite easily, and it's nothing but some constant over k squared plus 1 whole squared. It's not really a constant, but it's a k independent function. The fact that it's k independent is all that we care about, right? If it has some other dependence, we don't really care because we're doing integrals with respect to k. So as far as the integral is concerned, it's just a constant. But moreover, because this is the same C occurs here, here, and here, I can cancel it out. So when I do that, I will find that 1/2 of k squared over k squared plus 1 all squared minus 1 over 2 pi squared. Sorry, 2 pi squared of the integral over R3 of d3 k prime over k minus k prime squared k prime squared plus 1 squared is equal to the energy that we're looking for over k squared plus 1 squared. Okay. As an exercise, so use the fact that mod of k minus k prime squared is k squared plus 2k k prime cos theta plus k prime squared to compute the integral.
I just wanted to check. For the E into y take from this side of the board, doesn't that become x squared prime plus 1? So, so if you look at this side of the board, that's x y k prime. Isn't that k squared prime? Sorry, that's not k.
Yeah, the k prime only exists inside the integral, and it's taking care of that. So to show that integral is pi squared over k squared. Okay. And finally, I put all of this together to find that k squared over 2 k squared plus 1 squared minus 1 over 2 k squared plus 1 is equal to e over k squared plus 1 squared, which necessarily means that energy of the 1s excited orbital of the hydrogen atom is minus a half in natural units. H bar equals 1. H bar equals 1. This is what you would expect, again, by solving Schrodinger Equation position variables. Okay. So let me stop there. And next time I really will talk about the cost. Cost constant. So this idea of using an integral equation instead of a differential equation can sometimes be more powerful for exactly the reason that I've been harping on about for most of this course, which is that it furnishes integral representations of solutions to differential equations, where I can do a lot of things and read off a lot of the properties without actually doing the integral. In this case, I happen to be able to do the integral view, but you don't necessarily need to be able to do that. So the asymptotic properties can be read off directly from the integral equation. Okay, we'll come back to the integral equation and talk about how to classify them and how to solve them in some cases, and how you solve them in most cases. You can solve integral equations. Is to use integral transforms. The one thing you would notice is that if you'd approach solving an integral equation the way you would approach solving differential equations, you first have to isolate this phi, which requires you to differentiate the equation first. So the differential equation and then solve the differential equation. Very good. We'll see you guys next week then.